Hello, worldly crazy people out there. My name is Michael. I like wizards and dragons and making games, and welcome back to 3D Collisions in GameMaker. So far in this 30-something video series, I have talked about intersection tests between various 3D shapes, simply so that you can find out whether a collision happened between the two 3D shapes in question, and in the case of raycasts, where the collision happened. And today I'm going to talk about something that is very related, but at least the way that I'm going to attack it, it's going to be not quite the same as 3D collisions, and that is going to be terrain and terrain height maps. So, before I start, I want to be perfectly clear that it is completely okay to treat terrain as any other triangle mesh. Terrain is, after all, generally represented by an array of 3D triangles, and those triangles all happen to be approximately where the ground is, and you can sort those into a hierarchy if you want. You can sort those into a quad tree, oct tree, spatial hash, whatever you want. And that will work. That will allow you to test for 3D collisions between shapes and triangles, and do all the other things that you can do with 3D shapes. And if I were to simply load in, that wasn't what you saw on the screen just now. Wasn't the actual project. That was just an example I whipped up before I started recording. But if I were to load the terrain vertex buffer into the project, and if I were to set, 7 for a triangle mesh, one, you're going to notice a few things. It's going to take a long time, because the terrain in question that you saw was 64 by 64, and each of those squares in the terrain has 2 triangles, and that's going to be a total of 8,192 triangles in the vertex buffer. I think it's actually going to be a little less than that, because the number of triangles is 63 by 63, but never mind. So that took, 27 seconds to set up the terrain and sort it into the oct tree. And now when I zoom in, you can see that we can raycast into the terrain to get the hit location of the of where the mouse is over the terrain. If I were to bring in, for example, a axis-aligned bounding box, you could check for that against the terrain. You can see that this is a little on the expensive side. Our FPS_real is going down to the 40s when we're doing these things. That's a little annoying. The raycast appears to be more expensive than the AB. Good to know. And again, you can do that, but generally speaking, you don't want to drop your FPS down to the 50s just by detecting collision against the terrain. Again, if you're not using an oct tree, if you're using a quad tree or a spatial hash, I think a spatial hash would be ideal. That would perform a little better, but overall it still will be rather on the heavy side. So let me set that back. What you can do instead, and make no mistake about this, this isn't a universal truth or anything like that. This is just a way that I like to deal with terrain in 3D in games, with the kinds of games that I like to make. Oftentimes, you don't actually need fully fledged 3D collisions between terrain and any arbitrary shape. Oftentimes, all you really care about is the height of a terrain at any given location. And if you think, if you have the player jump in the air, and then when they land, if you check to see if the player's Z position is less than or equal to 0, then they're on the ground and they should stop jumping. If you think about replacing Z equals 0 with Z equals whatever the height of the terrain is at any given position, that's basically what I'm going to do now. I'm going to, I'll show a little visual example of what I mean on the screen right now, and I will get into a bit more of a test at the end of the video. But with the example you see on screen right now, we don't actually need any full 3D collision detections between the player and the terrain or anything like that. We really just need where the player's feet should or shouldn't touch the ground on the terrain. And so all I'm going to do is I'm going to create myself a new script. Let's call this call_Heightmap. And GameMaker did not freeze when I wrote that out this time. When I was testing this earlier, GameMaker froze when I did that, and I had to force kill it with Task Manager. That was a lot of fun. We can mark that as a constructor. I'm going to give it a few parameters in a minute, but first I'm just going to draw attention to one method that is going to be static GetHeight. And that's going to be a function which takes 2 arguments, an x and a y, and this is going to return the z value of the terrain at that position. Alright, that's all it's going to do. Again, this is not like a law of the universe or anything like that. This is just a thing that you can do with terrain in games that I often find is useful, and I think is useful enough to merit talking about in this series. This is just going to be a little bit of math, and it hopefully won't be that bad. So as for the arguments that the ColHeightmap is going to take, it's going to take 3. I'm going to give it a buffer. That's going to be a buffer of raw, basically terrain data. I'll get to exactly what that constitutes in a minute. I'm going to give it a width and a height, and we can take these 3 parameters to the constructor and save them as instance variables, like that. In my test setup, have I already added code that allows you to just plop down a terrain test in the world? I did. Okay, I had the foresight to set that up. All this is going to do is it's not going to check any collision against any other points or arrays or anything like that. It's just going to take a height map. It's going to have a ball, which is going to represent, for lack of better terms, the player. And you can move the player around, and the player's feet, or the ball's feet, or whatever, the ball's feet, amazing, is going to snap to whatever the height of the terrain is at its current position. And then in the draw event, you're just going to draw both of those so you can see them. All right. Right now, can I just have this return 0? Right now. Right now, it's just going to return 0, but I would like to run this, and I would like to show you exactly what this looks like. So we have the... Really? Oh. Knew I forgot something. If I run this now, and if I hit the tab key to bring up the terrain example, we have ourselves the terrain, and we have ourselves a little yellow ball, which is wandering around. And in an ideal world, when you move it around, it will snap to the height of the terrain at any given position. But we haven't implemented that yet. First, let me commit the Heightmap class, and I guess this would be a good time to talk about exactly what the terrain is. So I've added a few files to this project's included files. One is the terrain vertex buffer. This is just a vertex buffer. This was generated with my handy dandy terrain editor. This is a little program that I made. You can use it, and you can generate some noise on the terrain. This isn't the one that's in the game, but it's an example. And you can export this as a vertex buffer to load into your game and draw as a vertex buffer. That's pretty normal. I've also exported a height map, and a lot of times you might see a height map represented as, let me save a height map image, as a grayscale image like this. And if I were to open this in an image viewer, you can see, if you zoom in, this is just a grayscale image. Lighter regions correspond to higher values, darker regions correspond to lower values. This is a common visual representation of height maps. I'm actually not going to be using those. We don't need it to be encoded as an image, and to have all that extra image data, and to have a bunch of time wasted when the game tries to parse the image data. What I've instead done is I have instead exported a raw data buffer of height values. So the raw data buffer essentially contains an array of 32-bit floats corresponding to the height of the terrain at any given position. And the way that those are arranged are, I'll throw another chart on the screen right now, I suppose. If you have a 4x4 height map, for the sake of brevity, the first value in the data buffer is going to correspond to the upper left. So that's going to be position 0, 0 in the terrain if you index the x and the y-axis by 0. The second value in the data buffer is going to be the one below that, so it's going to be position 0, 1. The third value in the terrain is going to be the position below that, 0, 2, and we are going to continue down each column in sequence, like this. Whether you go row major or column major for these things really is not super relevant. I, for any arbitrary reason, when I designed this thing a number of years ago, chose to have columns, to have a column major. And what this means for us is that if you want to be able to access the value in a cell at any given position, so if you want to be able to find a value at, for example, let's say 3, 1 in the terrain, that's going to be this highlighted cell here. To find that cell, you can take the x value that you're looking for, multiply it by the terrain's height, and add the y value. So that's going to be our x is 3, our height is 4, our y is 1. So 3 times 4 plus 1 is going to give us an index of 13 that we're going to look up in the height map, and that is indeed the index in the height map's data buffer, which corresponds to position 3, 1 in the cell. All right, so remember that little equation: x times height plus y. We are going to come back to that. I'm going to close this terrain editor because I think I'm done with it for now. In this 3D collision test program, I have simply loaded in terrain.hm as our terrain height map data, and I've stored that in a buffer, and that's what's being passed to the call test height map as the second argument when you hit the tab key, and that is the data buffer that is passed into the ColHeightmap constructor when you create a new one in this example. And again, the width and the height are 64 by 64. Mine is square. It doesn't necessarily have to be square. So that brings us to the GetHeight method of the ColHeightmap. Let me full screen this. I'm going to do a few things to set up. First, I'm going to say x is going to be constrained to a position that's actually within the height map, because if x is less than 0 or if x is greater than the width, then we're going to have problems. So I can say x is going to be clamp between x 0 and self.width minus 1. Same for the y. So we're going to say y is going to be clamp between the original y position passed in as an argument between 0 and self.h minus 1, not y. Yes, you can reassign values of arguments to functions. I get the feeling that a lot of people assume they're constant and don't know that you can do this, but you totally can. And I'm also going to say x is going to be equal to floor of x, and y is going to be equal to floor of y. And this is not going to be final code. I'm just going to do this so that we don't have anything extremely weird happening to our height value. Let's say next, I'm going to say index is going to be what I said before about x times self.height plus y. And that is going to be our index in the height map buffer that we're going to look at. Again, this is not completely going to be final code, but I'll talk about what happens if you make a very common and easy mistake to make. And lastly, we can say var z at this position is going to be buffer peak. We're going to look at self.buffer. Our offset is going to be index, and our type is going to be buffer underscore f32. I do love my long and ridiculous variable names, don't I? So if I run this, this is not quite going to do what we want for two reasons. I will give you about maybe 30 seconds to see if you can spot them. For one, if I move around, you're going to notice that we have our z position doing something. It is often not the z position of the actual terrain that's beneath our feet. And you might wonder why that is. And if you're familiar with things such as pointers in memory and the sizes of data types versus array indices, you may notice that we did not do something, and that is that we did not compensate for the actual size of a 32-bit floating point number in the buffer. So I will assume that everyone watching this already knows how buffers in GameMaker work, but we're looking at a raw memory address here, or at least kind of sort of close to a raw memory address when you're using GameMaker. You don't really deal with those things. And we are going to need to multiply our index by the size of a 32-bit float, which is 4 bytes. Because each of these values is going to take up an entire 32-bit floating point number. It's going to take up an actual 4 bytes in the buffer. So you're going to need to multiply the index by that size. If you really want to be thorough, you could say buffer size of, buffer f32, and that's going to give you the size of any given data type. For example, a 32-bit float. This is roughly equivalent to C and C++'s size of macro. And if you wanted to, for example, have a height map which stored its height values as something else, for example, a 64-bit float, or I don't know, a 16-bit int or something like that, depending on what your game needs, you would want to remember the size of that data type. I guess, let's call this data type size, and we can define that down there. You could hard code the value if you want to. Most of the time, 32-bit float is probably fine, but hard coding things makes me uneasy. That already did give me a bit of extra work to do at an earlier point in the series when I assumed that we would be using quad trees for our hierarchies. And now, when I move the ball around, when I move the player around, being very generous with the term player here, you can see that our height is approximately equal to the height of the height map at any given position. And you might notice that it's still jittering around a little bit. It's still very, it looks like it's snapping to certain positions, you might think. And that is because it actually is snapping to certain positions, because we are basically rounding the position of the XY that we're looking for in the height map to a, basically rounding it down to the nearest integer when we floor them here. And our position that we're checking can be anything. It doesn't necessarily have to be an integer. It can be like 1.5 or 5 point something else, some decimal. And if you look at the visual model for the height map, you can see that it is in fact sloped, and we are not simply aligning our positions in between the cells to. We are in fact connecting those points with triangles. All right, so I'm going to commit what we have now. And when I'm done with that, I'm going to make this a little bit fancier. So instead of simply rounding the position that we're looking up in the height map, we can instead basically sample from all four corners around us. So X and Y rounded down and rounded up, and we can essentially interpolate between them. And that will give us a smooth value. So we can interpolate between the four corners of a height map cell. To do that, I'm going to, instead of saying x equals floor of x, y equals floor of x, I can say var, let's say x1 is going to be, x1 is going to be floor of x. We can say var, actually I'm going to call it x0 for reasons that you'll see in a minute. Y0 is going to be floor of y. Var x1 is going to be floor of seal of x. And var y1 is going to be seal of y. So I'm going to take x and y rounded up and rounded down, as I said. X0 and Y0 is going to be the basically the previous corner of whatever cell we're in. X1 and Y1 is going to be the corner that can be found to the bottom right. Okay, next, instead of simply getting the index of a single position and sampling from that single position, let's move this data type size up to the top so it's out of the way. Instead of doing these two lines once, we are going to do these two things for each of these four corners. So upper left, upper right, lower right. I can say var index, I'm going to call it 0, 0, is going to be x0 times self.h plus y0. So index 0, 0, x0, y0, we can say var index 0, 1 is going to be x0 times self.h plus y1. And we can do this two other times for the other two corners of the containing square. And because I don't actually feel like typing out z at this position, such a long variable name, I'm just going to say var z00 is going to be buffer peak self.buffer index 0, 0 times data type size and a buffer f32. And again, we can do this 4 more times, 1 for each corner. Let's see, that's going to be 0, 0, 0, 1, 1, 0, 1, 1. Like this. So now we have our height at the four corners, the four nearest corners on the terrain, and we can start interpolating between them. So I can say var, let's say z underscore top. We're going to first interpolate horizontally between the upper left corner and the upper right corner. So that's going to be 0, 0, and 1, 0. So we can say lerp from z0, 0 to z1, 0. And the amount that we're going to interpolate by is going to be the decimal part of the x value. And you can get the fractional part of a number by saying frac of x. You can also just say something like x mod 1 or x %1 if you're a fan of the mod operator. I'm going to go frac because it reads out loud as I would say it. The fractional part. We can say z underscore bottom is going to be interpolating z01, z11 by the same amount. So z top is going to be the height of the height map at the top of the square that surrounds your point. Z underscore bottom is going to be the height of the terrain at the correct x position at the bottom of the terrain. And we can say var z, let's call it z final, is going to be lerp between z underscore top, z underscore bottom, and the fractional part of the y. If you've ever tried to do things like manually sample a color from a texture, you've probably done something similar to this. We're going to return z underscore final. If you want to think of sampling from the height map as sampling from a texture in a shader, you can do that. We are using linear interpolation here, which is basically linear texture filtering in GameMaker and computer graphics. You could use other interpolation methods. You could use, I forget exactly what smooth step interpolation uses. Sigmoid. You could do something like that instead of a lerp if you want, but this is going to be fine for our purposes. I'm going to run the game. I'm going to bring up the height map, and I'm going to have this ball walk around the terrain, and you can see that its traversal up and down the hills and the slopes is much smoother than it was before. No more jittering up and down. We are now snapping our position to exactly the position on the terrain instead of like rounding it to the previous integer. All right. So this is, as I said, I find it often useful. This is not the extent of what you can do with terrain in games, but I think it's going to be the extent of what I do with terrain in the series. I will have something resembling an in-game demo at the end of this video. Some comments. You may notice that this is much faster than doing any collision detection with actual shapes and with actual terrain and quad trees. You may also notice that when I brought up the terrain shape, it was instantaneous, and we didn't have to wait 27 seconds for the terrain height map to load, as we did when it was a collision shape, because we didn't have to assemble the quad tree or the up tree or anything like that. Big advantage there. Again, all we're doing is checking for 4 values in a buffer, which is extremely fast. This is one of the fastest like individual operations you can do in GameMaker. And we are simply lerping between them a few times to get you an exact value. Contrary to a lot of the other collision detection math that we've done, where we have to do a lot of vector operations and like vector adds and like a lot of loops and things like that to figure out, for example, the separated axis theorem with this case the call ob. All you have to do is check for values and lerp between them a few times. So checking for a value in a height map is extremely fast. And I would definitely say that if this is something that you can get away with in your game, and if you don't need to have objects doing precise collisions with the ground, you should absolutely do this. But on the other hand, if you're making a game where you do need precise collisions with the ground, maybe you're going to have like a ball bounce off of it, and it's going to have to like raycast and reflect off the normal of whatever it hit, then this isn't really going to get you very far, unfortunately. You could still use it for some things, but in cases like what I just described, you will need actual collision detection with terrain. Alright, one more thing of note. Everything in this project besides this one line here will be just automatically picked up by the GameMaker garbage collector. You don't have to do anything like manually destroy structs or anything like that, or arrays or anything like that anywhere else in this demo program aside from the vertex buffers, but that's really just there for testing. But the data buffer for height maps will have to be garbage collected. If you create a bunch of these, for example, whenever you enter a map and you load a terrain buffer, you're going to have to remember to delete this. It may be wise to add a static delete function method to to the terrain height map. Do I want to do that here? I guess I will. Buffer destroy, buffer delete. Thanks, GameMaker. Just to remind people that it's a good idea to do this. If you ever finish with a height map, you will want to delete its data buffer. In this example, don't have to worry about that because the height map buffer is just recycled every time you instantiate a new call test height map, but just remember that. GameMaker in recent days has been moving away from data structures that you have to explicitly destroy with structs and arrays and all that, but if you're using a buffer like this, you're still going to have to think about that. That said, you can convert this to an array, so you can just read out every value in the height map and put it in an array instead. And that would take care of the problem of having to manually delete them, and it would also take care of the problem of having to worry about the data type size when you sample from the height map, but I don't think I'm going to get into that here. That's going to be another step. It's going to slow the game down slightly when you create a height map. Although reading from an array is almost as fast as reading from a buffer. But if you do prefer that, you can convert the buffer to an array. Alright. One more thing before I forget. So each of the terrain cells in this height map is 1. And that's fine. When I run the game, if I zoom in, you can see that every cell in this terrain takes up 1 world space unit. And that's fine on its own, but if you have, for example, if you want to scale your terrain, so if you don't want the terrain to be this dense, if you want to have your terrain be, say, 100 times bigger, you are suddenly going to need to remember to scale your X and your Y positions that you're checking from accordingly. I think the simplest way to do that is going to be to add a, for example, scale value to call Heightmap, and we can take another parameter to the constructor and say self.scale equals scale, and then that's going to be a scale factor when we do things such as draw the Heightmap, draw the terrain. Let's make the scale 10, not 100. We can give it a scale of 10. When we draw the terrain, the matrix transform can get a X, Y, and Z scale of. Alright, so if we were to draw the height map with that scale, if I were to run the game now, we would be getting the wrong answer when we're looking at the terrain. As you can see, we are now scaled up by 10 times. That's pretty big. I'm going to move the player thing around, and as we can see, we're getting slightly the wrong answer. Yeah, that's not very helpful when we're trying to get the position of the player at that terrain. But inside the GetHeight method, we can say x divided by equals self.scale, y divided by equals self.scale, and we can also return the final value multiplied by the scale, because scale is uniform here. It's going to be the same on x, y, and z. So now, if I were to bring in the scaled height map and move the player around, we can see that we are still hugging the ground. No matter what the scale of the terrain is, if I were to set the scale to something else, it would still work. This is something that may be useful to keep in mind if you have a terrain which is very large and which is not necessarily one-to-one with the scale of the world. Because if we're being realistic, if your game is assuming that, as I often do, 32 world space units equals 1 meter, then having the terrain be as dense as 1 triangle every world space unit is a little bit extreme. Alright, but I think that's going to be all that I do here today. If you want the code for this, look for the GitHub repository down in the video description. I actually don't remember which week this is. I think it's 31, but I'll have to double check, because I know a couple of the previous ones were like not kind of off the record, off the main project. Oh, I still have to like add quad trees to this, don't I? Anyway, look for the GitHub repository down in the video description. Next time, I'm going to talk about spatial hashes. I've mentioned them a few times. I've been procrastinating throwing together a video on them. I don't know, terrain just seemed more interesting this week for whatever reason. After that, I'll talk a little bit about camera frustrums and frustrum culling, and then it'll be it for 3D collisions in GameMaker. What an ordeal this has been. So, if you want to see more like this, I try to post about 2 game dev videos a week, one tutorial like this, and one let's make a game, currently 3D Wizard game. We'll be using this 3D collision system in it at some point in the near future. I have a Patreon, so if you want to contribute to the channel, links to that can be found in all the usual places. Otherwise, I hope you all found this useful, and I will see you all later. Special thanks to Army Armbuster, DJ Gibbles, Edward Holt, GameMaker, Gamer Player, Harold Gidry, Manta Ray, Project 103, Rowdy Coder, Syndra Larson, Squarecrow, VTroV, and Zenjament for supporting these videos. If you want to contribute to the channel, head on over to the Patreon page down in the video description to join the fun.